welcome back to my channel. Today we're going to be looking at a sample internal assessment for Pure Math Unit 2 Module 2. This can also be used as a practice for your Pure Mathematics exam which is coming up. Now without further ado, let's get right into it. It says the population of a town is 25,000 at the end of year 1. A model predicts that the population of a town will increase by 3% each year. Determine the predicted population at the end of year 2. So you have the population at the end of year 1. So that's the first year. For the first year, it's 25,000. Alright, now for the second year, it's going to increase by 3%. Now, this can be worked out quite easily because this is what is happening. At this moment, this would be 100% of the population. When 3% goes on it, it becomes 103% in the second year. Now, of course, we can convert this to decimal to work with it much easier by dividing this by 100. So my decimal value is 1.03. So all I need to do is to take the population for the first year. To increase it by 3%, I simply multiply it by 1. So it's going to be 25,000 times 1.03. Alright, of course here we have our calculator open. So I'm going to have 25,000 times 1.03. That gives me $25,750. Alright, so this is going to be equal to $25,750. Now this represents my population at the end of the second year. That is the amount of persons that are going to be there. Alright, good so far. Let's move into part B. It says the model predicts that year N will be the first year in which the population of a town exceeds 40,000. Okay, let's go down and get some space. Show that n-1 log 1.03 is greater than log 1.6. Alright, so how do I work this out? Clearly what's happening here is that I'm constantly going to be increasing by 3% each year. So I'm always going to be multiplying by 1.03 to keep it going to get the next value. So you have the first value, which is 25,000. You have a second value, which is 25,700 and 750. So first, second, to get the third year, this is now my 100%. So I'm going to have to multiply it by 1.03 to get the population in the third year. And you keep on multiplying. Now, what series come to mind or what progression comes to mind? It should be the geometric progression. Once I keep multiplying by something, now the geometric progression says that an is equal to ar raised to n minus 1. Now, of course, in this case, they're asking us to use n, which would be the number of years, as capital N. So that's the difference here. Alright, so I'm going to have AR. Now I'm going to change that n to the capital N, n minus 1, should exceed. Exceed means greater than 40,000. Alright? Alright, now let's put in the information that we have. A represents the first term, which is the first year. How much was it in the first year? The question told us it was 25,000. Alright, R, of course, I'm going to constantly be multiplying by 1.03. So I'm going to have 1.03 raised to n minus 1 should be greater than 40,000. As we know, exceed means greater. Alright, what do I do next? I need to find n. I need to transpose this, or I need to break this down. So what I'm going to do is that I'm going to get rid of this 25,000 that is right here before we can take down the n minus 1. So I'm going to have 1.03 to the n minus 1 is greater than 40,000 divided by 25,000. So this boils down to give me 1.03 to the capital, and of course this capital N minus 1, because they said after n years, and that's capital N, is greater than. Alright, so we have 40,000 divided by 25,000, which is going to give me 1.6. Alright, and we could plug it in the calculator, but we don't need to. Now, in order to get this power down here, I'm going to have to apply logarithm. So we can log both sides, right? So I'm going to have log of this side is equal to the log of this side. Alright, of course, log without a base is base 10, as you know. So what's going to happen is that the power, which is n minus 1, and because it's more than one term, I have to put it in a bracket, comes to the front. I'm going to have log 1.03, and this would be greater than log 1.6. And of course, you get your 4 marks there, total of 4 marks. So that wasn't so difficult at all. Be careful when transposing, especially when it comes down to log, because I could have logged it from the start here, but if I had logged it here, I would have to apply the laws of logarithm. All right, so I would have done less work by dividing by the 25,000 first and then applying log. All right, then of course part C follows up to say find the value of n. So what it means is that I'm going back for my expression here that I had just proven, that n minus 1 open bracket log 1.03 is greater than log 1.6. Now what do? I want n. n minus 1 is multiplying log 0.3. So of course I need to divide both sides by log 1.03. Alright, log 1.03. So n minus 1 is equal to, let's see what happens here. Now I can go to my calculator and divide log 1.6 by log 1.03. Alright, so I'm going to have log 1.6 divided by the log of 1.03. Here we have 15.9. So let's go back. So this is going to be 15.9. So n would be equal to 15.9 plus 1, which would be equal to 16.9. Now, what does 16.9 really means to you? 16.9 means that I have completed 16 years and I'm now in my 17th year. All right. So really, how long does it take? N would actually have to be 17. All right, because you're already in the 17th year. So n would be equal to 17 years. All right. So after 17 years, it would exceed that value there. All right. Let's take it down to the next question. So we have 17 there. It says at the end of each year, a donation of $1 will be made to charity fund on behalf of each member of the population. Assuming the population model, find the total number that will be given to the charity fund for the 10 years from the end of year 1 to the end of year 10, giving your answer to the nearest 1,000. Alright, good. So remember now, in the first year, the population was 25,000 at the end of the first year. So what it means is that $25,000 would have been given to charity. At the end of the second year, the population was 25,750. So it means that 25,750 would have been given to charity. And this keeps going on and on and on and on and on. Now, what they want is a total amount, and that is the imperative term here, that would have been given to charity from the end of the first year. So they want you to sum the first year plus the second year amount plus the third year amount, and it goes on and on like that. Which means that I'm going to define the sum of this geometric series. So let me go to the formula. All right, so we're going to have Sn equal A into r to the n minus 1 over r minus 1. And they said when r, which is a common ratio, is greater than 1, we use this formula here. Although the other one will pretty much give you the same value. Okay, so I'm going to have Sn equal A, which is the first term, that's going to be 25,000. R 1.03, n which is 10 minus 1 over 1.03 minus 1. Alright, so in this case, I simply just need to bring up my calculator and I can put all of this in my calculator all at once. So let me go. On my fraction bar, I have 25,000, open bracket, 1.03 raised to the 10 power, alright, good, minus 1, close bracket, over, let me go down, over 1.03 minus 1, and all this boils down to 286,596, or if I, well, 286,596 and 98 cents. So 286,596.98. But of course, they said to the nearest thousand. Don't forget that part. So this is a thousand position. This is 5. 5 or more means you round up. So I can say this would be $287,000. Right? Remember, without the dollar sign, it's not money. Money is what tells me that. The dollar sign is what. Alright guys, we move to question 2. It says show that r over r plus 1 minus r minus 1 over r is equivalent to 1 over r into r plus 1. From the moment we look at this, we know that this is pointing at what we call the sum of a series by method of difference. So we know the follow-up questions to expect. Now the first part is pretty straightforward. All you're saying is that show that when I simplify this side, it is going to be equal to the right hand side. So I'm going to be taking the left hand side, which is r over r plus 1 minus r minus 1 over r, right? Now this is fraction, I'm subtracting fractions, so I do exactly what I would normally do. I start by finding the LCM, which is r plus 1, make sure you have that in a bracket, times r. Now r plus 1 into all of this would simply give me r, and r times r is r squared. That is taken care of. R into this, r would cancel r, so you have r plus 1 multiplied by r minus 1. Now there are certain things in maths that you need to be able to pick up on right away, like the difference of two squares. So this is going to become r squared minus, open bracket, r squared minus 1 all over r into r plus 1. Alright, let me take it to this side now. Now let's clear the bracket. We have r squared minus r squared. 2 minus here gives you a positive 1 over r into r plus 1. So I'm going to end up with 1 over r into r plus 1. Now notice how I switch the r plus 1 and the r because multiplication is commutative, so that's no problem there. Alright, so easy 2 marks for you to get. Part B, hence using the method of difference, find an expression in terms of n for this. Alright, there's an easy way that I can condense this. I can simply say that this is really the sum from r equal 1 up to n of 1 over r into r plus 1. Alright? The reason why you have n up here is because this is the n term. This is the very last term. This is the term you get when you put in n. I'll draw this properly. Now, of course, I'm going to go back to part A. Bear in mind that this would have been equivalent to r over r plus 1 minus r over r minus 1. Alright? So this is equivalent to the sum from r equal 1 up to n of r over r plus 1 minus r minus 1 over r. So the idea is that if I can find the sum of the left hand side, I can find the sum of the right hand side as these two are equivalent. Alright, so let's apply the method of difference. So to get the first term, of course what I would do is simply put in 1 in there because it starts from r equal 1. Notice how the denominators down here, this would really be 1 times 2. Then you're going to have 2 times 3. Then when you put 3 in there, you're going to have 3 times 4. And it keeps going on and on and on like that. So in method of difference, I'm using the right hand side. So I'm going to put 1 in here. If I put in 1, I'm going to have a half minus 0 over 1. Plus sum of, which means I keep adding. So this is my first term. My second term is when I plug in 2. So I'm going to have 2 over 2 plus 1 is 3. Minus 2 minus 1 there is going to give me 1 over 2. Alright, please understand the concept. So instead of putting 1 into this side and keep going on and on, I'm using the expression that is equivalent to, which is this expression. They mean the same thing, they're both equivalent. And the use of this one is that this is applying method of difference, so I can use the pattern to deduce what the sum of this expression is. To get my next term, I'm going to put 3 in there. Alright, if I plug 3 into that, I'm going to have 3 over 3 plus 1 is 4, minus 3 minus 1, which is 2, over 3. That's 2/3. Alright, so I know what's going to happen at the lower end. Now I'm going to write the last 3 terms to have an idea of what's going to happen up there. Now let me start with the last term. The last term, of course, is when I plug n into the expression for r. So I'm going to have n over n plus 1 minus n minus 1 over n. Then the second to last term, if when I plug in n I get the last term, what do I plug in to get the second to last term? It must be n minus 1. So I'm going to have n minus 1 over, if I put n minus 1 here, n minus 1 plus 1 is simply n. N minus 1 is n minus 2. And then you have n minus 1. Alright? What about the third to last term? Alright, I'm just putting 3 terms for you to get the understanding. Which is when you put in n minus 2. So if I put n minus 2 here, it's just going to be n minus 2 over n minus 2 plus 1, n minus 1, minus, if I put n minus 2 here, so it's n minus 2 minus 1, which is n minus 3 over n minus 2. Now, let's look for the things that would cancel out. See, a half is gone, 2/3 is gone. Of course, you realize what is coming after is canceling the one that comes before. So it means that this will be cancelled out as well by the term that comes next. Alright, let's look at the upper end. This takes that out. This and this is gone. Alright. This, of course, there's nothing to take this out because there's nothing that's going to come after. Alright, but what would come before this, and the next time we take this out. So all you'll be left with is n over n plus 1. That would be the sum of my expression here. And you can write a final statement to say that. Very important. Cool. Part 2. Find the sum from r equal n plus 1 up to infinity of all of this. Or show rather, that the sum of this is equal to 1 over n plus 1. Okay. Of course, I'm going to need what I did just now to do that. But let us say the formulas as we have them, the sum of any expression starts from r equal 1 and it sums up to a point. That is what we found the formula for, from 1 up to any point. The problem with this is that this is not starting from 1. So I have to make it start from 1. So I'm going from n plus 1 up to infinity of 1 over r into r plus 1. So what I'm going to do, I'm going to have to rewrite it, go from 1 up to infinity. Alright, if I'm going from 1 to infinity, and I want from n plus 1 up to infinity, I'm going to have to subtract what I don't want. I don't want it from 1 up to n. Of course, you do understand the formulas sum from 1 up to a point. So you have to always start from 1. Alright, so now we know what the sum of the formula is already. The sum of the formula is what we found up there, which is n over n plus 1. So let me just highlight that here. That the sum of 1 over r into r plus 1 from 1 up to n is equal to n over n plus 1. This n here represents any number you want to put up there. It doesn't matter. Infinity, anything at all. The only problem is that it must start from 1. Alright, so how do I work it for this one? This one is going, you can't, infinity is not an actual value. It's a concept. So I'm going to have to use a limit as n tends towards infinity on this one. Alright, so I would plug infinity in the place of n, but infinity is a concept. So I'm going to use the limit of it tending to infinity of n over n plus 1. Minus this one, the sum of this is really n over n plus 1. So I can plug that in, that's not a problem. Alright, now when evaluating a rational function to infinity, to evaluate that, we divide through by the highest power of the variable in the denominator first. So I'm going to have the limit as n tends towards infinity of n over n plus 1 over n. Alright? And minus n over n plus 1. Alright. Now, when you break this down, you end up with a limit as n tends towards infinity of 1 over 1 plus 1 over infinity. Alright, let me take this out because I'm going to plug in the infinity so I don't bring this back. Alright, so that's 1. So all this is really 1. Now 1 over infinity is going to tend towards 0. So that's out. Minus 1 over minus n over n plus 1. Alright, let me create some space here and work that out. Now I can put 1 over 1 minus n over n plus 1. The LCM is n plus 1. So 1 into n plus 1 is going to give me n plus 1 minus n plus 1 into n plus 1 is 1. 1 times n is n. So I simply have 1 over n plus 1, which is what we exactly wanted. Alright, QED. Alright, we move into question 3, and it says a series of positive terms u1, u2, u3 is defined by u1 equal to 6, un plus 1 equals 6un minus 5 for n greater than or equal to 1. Prove by induction that un is equal to 5 times 6 to the n plus 1. Of course, you have two different formulas. You have the recurrence relation formula, which is this, and you have the n-term formula, which is this. Now, the first formula is based on what comes before. So, if I want to find the 10th term, I would have to find all the terms before that. The n-term formula means I simply take 10, I put it in the place of n, and I have the 10th term. Now, from the recurrence relation, we know that u1 equal to 6. So we're going to prove true for n equal 1 using the n-term formula. Alright, so I'm going to have u1 equal to 5 times 6, the 1 minus 1 plus 1. This is going to give me u1 equal to 6 to the 0 is 1, 5 times 1 plus 1, that's 6. So it's true for n equal to 1. And then we have to assume true for n equal k. So I'm going to have uk equal to 5 times 6 to the k minus 1 plus 1. Alright, I don't need a bracket because, of course, multiplication comes before addition. Now, once you have assumed it's true for n equal to 1, you're going to have to prove it for n equal, assume true for n equal to k, you're going to have to prove it for n equal to k plus 1. So, let me go here. So, prove for n equal k plus 1 that uk plus 1 equal, and this is going to be equal to 5 times 6 to the k plus 1, well, plus 1 there. So that's what I should get when I'm finished. But now let's go back up. How am I going to prove that? This is where the recurrence relation comes in now, because the recurrence relation tells you that the connection between the k term and the k plus 1 term is this. So I can say that uk plus 1 equal to 6 uk minus 5. Okay, let's get into it. Now uk, you know it already. You have it in the assumption step. So it's going to be 6 open bracket. uk is 5 times 6 to the k minus 1 plus 1. And of course, you put the minus 5, which is there. Alright, let's map this out. Now you have 6 times this time. Let me clear the bracket because I know sometimes persons tend to get confused with how they expand this. So it's going to be 6 times 5 times 6 to the k minus 1 plus 6 times 1 is 6. And then of course you have your minus 5. Now by laws of indices, you can, when you in fact, we can regroup this so we can turn this around, alright, because multiplication is commutative. So by laws of indices, when you multiply two things with the same base, you add the powers. So I'm going to have 6 to the k plus 1 minus 1, or I could write 6 to the k minus 1 plus 1 and then rearrange it. Alright, plus 6 minus 1, 6 minus 5 is 1, so plus 1. So let me take it down now. Alright, so, and this is exactly what we wanted. Oh, I left out the 5, my bad. So I'm going to have 5 times 6 to the k plus 1 minus 1. So that's what we wanted. So we can say proven true for n equal 1, n equal k, n equal k plus 1, and hence for all elements in the natural number system. Alright, that's an easy amount of marks to get. That's all of 8 marks. Very easy 8 marks to get. Alright, we take it down to question 4. Question 4 says f of x is equal to x cubed minus 7 over x plus 2, where x is greater than 0. And there are some concepts that you can see here that make sense. It says show that f of x equal to 0 has a root in the interval. Alright, this is what we call now the intermediate value theorem, IMVT. Alright, and it says that if f of x has a root, I'm going to call it alpha, between 1.4 and 1.5, then f of x, or f of 1.4 times f of 1.5 is going to be less than 0. So all I need to do is find f of 1.4, find f of 1.5, and see that it's equal to, is less than 0, right? Let me bring up the calculator. So this would imply then, let me bring up the calculator. Alright, so on. So I'm going to have, so all it means is that wherever I have x, I'm going to put 1.4, right? So I'm going to have open bracket, 1.4, close bracket, cubed, minus 7, fraction bar, 1.4, then plus 2, that's negative 32 over 125. It's negative 32 over 125 times. Now to get f of 1.5, I'm not going to do it all over. I'm just going to go back and change the 1.4 to 1.5. So let me go back. So delete. I'm going to have 1.5 there. Back. Delete 1.5. That's 17 over 34. Alright, so this is negative times positive, which is indeed going to be less than 0. So you can write the statements. Alright, so we know it's less than 0 because I'm multiplying a negative by a positive. Alright, so that part is good there. Okay, let's take this down some more now. It says use x1 equal 1.4 as the first approximation to the root. Apply the Newton-Raphson procedure once to find the approximate value of alpha to 3 significant figures. Alright, let's talk about Newton-Raphson. Alright, so one of the best way of approximating the root of an equation. And it says that xn plus 1 equal xn minus f of xn over f prime of xn. Alright, that's what Newton-Raphson says. Alright, now we know what xn is already. So it's like finding x2 then and knowing x1. So let me rewrite this. So it's really saying that x2 is equal to x1 minus f of x1 over f prime of x1. Now what it means is that you're going to have to differentiate it, right? So bear in mind, let me go back for f of x. So let me go up a lit. F of x was x cubed minus 7 over x plus 2. That's x cubed minus 7 over x plus 2. Alright, so I'm going to have to differentiate this, which means all I need to do is bring up the x here. So I have, let me rewrite it first. So it's 7x to the minus 1 when it comes up plus 2. So f prime of x would be 3x squared minus, of course I bring the minus 1 to the front, it's going to give me a positive 7, x to the minus 2, right? So let's see what happens here now. I'm going to plug it in, so I'm going to have, this would be, so let me say x2 equal 1.45 minus, and it says f of x over, so f of x, all you're going to do is replace x in this with 1.45, so I'm going to have 1.45 cubed minus 7 over 1.45 plus 2. Alright, same thing down here. F prime of x is this, that's 3 times 1.45 squared. Alright, plus, of course, plus 7 times 1.45 to the minus 2. Alright, Now all this can be done with a calculator, alright? Calculator works. So let's throw all this inside the calculator. So I'm gonna have 1.45 minus fraction bar. I'm gonna have 1.45 cubed minus 7 over 1.45, and of course plus 2 all over. Alright, so I'm gonna have 3 bracket 1.45. Of course, this is squared. Plus 7 open bracket 1.45. I'm going to raise that to the minus 2. Right, I'm going to go forward and delete this. So close bracket, raise to the minus 2. That's 1.42 or 1.4, and it says the 3 significant figures, so it's 1.43. Alright, so x2 equal to 1.43. Now remember the intermediate value theorem. The intermediate value theorem said the root must be between, and if it's not between, you know something is wrong. It should be between 1.4 and 1.5. So we have an approximation there. So that can work. Alright. Question C. With the interval 1.4 to 1.5, use the interval bisection method twice to obtain an approximation, giving your answer to 3 significant figures. Alright, with interval bisection, it believes that if you keep bisecting the interval between where the roots lie, you keep getting closer and closer to the root. Let's see if that is true. 1.4, 1.5. Alright. Now, what I need to know is that the root is always between a negative value and a positive value. So initially when I had plugged in 1.4, I'd gotten a negative value, and 1.5 had given me a positive. So all I'm going to do to make this easier is to put the negative sign there, positive sign there. Alright. Now interval bisection, as it suggests, means I'm going to add the intervals and divide it by 2. So let me say x1 would be 1.4 plus 1.5 all over 2. Now this is actually going to be 1.45. Alright, so it's going to be in the middle. So what I'm going to have to do, I'm going to have to plug in 1.45 in the original function to determine what the sign is, whether it produces a negative or a positive. So let me pull up the calculator here now. Alright, so on. So I'm going to have 1.45 cubed minus fraction bar 7 over 1.45, and I'm going to have the plus 2. So that's 0.22. What is not important to me, the value. What is important to me is the sign. Although by some extent you realize that the value keeps getting closer and closer to 0, because I want it to be as close as possible to 0 so that I know it's actually close to the root. So this is a positive. So the root is now between 1.4 and 1.45. So I can say that x2 is equal to 1.4 plus 1.45 all over 2. Alright, let's go back to the calculator. Alright, so on 1.4 plus 1.45 over 2. 1.425. So it's going to be in here. Alright, and now I'm going to have to plug 1.425 in the calculator to determine the sign. So up here, probably I should have said f of, well, I already have that to indicate that. So I'm going to plug 1.425, so 1.425. which I'm not going to have to plug in the calculator to determine the sign. So I'm going to have 1.425 cubed plus 7 over 1.425 plus 2. Oh, sorry, there should be minus. Alright, that's pretty close. Alright, it's closer than my previous value. And of course, the sign for this would have been negative. So the root would have been between these two now. Alright, so since this is even closer, I'm going to assume that the root or alpha is approximately 1.425. Alright, we're moving to question 5 on the internal assessment for Peer 2, Module 2. And it says use the binomial theorem to expand the expression 8 minus 3x all raised to the 1/3, where mod x is less than 8 over 3. Alright, now this means this is a value for x for which the expansion is valid, and that is important in ascending powers of x up to and including the term x cubed. So let's start with a general expansion. The general binomial expansion is 1 plus x all raised to the n, and of course this is also the Maclaurin expansion for when the power is a negative or a fractional power. So this is equal to 1 plus n over 1 factorial times x plus n into n minus 1 over 2 factorial x squared plus n into n minus 1 into n minus 2 over 3 factorial times x squared. Of course, this continues to infinity, but we're going up to x cubed, right? So this should be x cubed. All right, now in order for me to expand this bracket, I'm going to have to do a comparison. So I need to make it look like this, 1 plus something. All right, what do I do? So you have 8 minus 3x raised to the 1/3. All right, first of all, I need to have 1 here so it can look similar. So what I'm going to have to do is that I'm going to have to factor 8 out of the bracket. But by laws of indices, if I'm going to factor out 8, I'm also going to have to take the power, which is 1/3 with it. So I'm going to have 8 to the 1/3, and I'm going to have to divide each thing in the bracket by 8. So this is actually 8 into 8 will become 1. So I don't have to show the division for the process, right? So we understand it. 8 into 8 is 1, and 8 into this would be 3x over 8. And of course, this is raised to the 1/3. Now, a to the 1/3, if I raise a to the 1/3, I'm going to get 2. So I have 2 times 1 minus 3x over 8 all to the 1/3. Now, let us identify certain things here. By comparison, in the place of x, you have negative 3x over 8. And in the place of n, you have 1/3. So that is what we're going to use to populate the function here. Let me just scroll down a bit here. So this is actually going to become, oh wow, I'm going into a space. This is actually going to become, let me see if I can do this in one line now. This would be 2 multiplied by the entire expansion, which I'm going to put inside of this bracket here. I'm going to have 1 plus n is 1/3, so I'm going to have 1/3 over 1 factorial. In the place of x, you have negative 3x over 8, so I'm going to have negative 3x over 8 here, plus n into n minus 1, so I'm going to have plus 1/3 into 1/3 minus 1 all over 2 factorial. In bracket, I'm going to have negative 3x over 8, and of course this is going to be raised to the second power. And then the final term in the expansion, as we're going up to x cubed, would be 1/3, in bracket 1/3 minus 1, in bracket 1/3 minus 2, all over 3 factorial. Of course, all this is going to be multiplied by x, and what is playing the role of x in this case is negative 3x over 8. Alright, and this is going to be raised to the third power. Alright, let's see what we make of this. So I'm going to have 2 multiplied by, and I'm going to simplify this bracket. Alright, now if you're afraid to work this out, you can make your calculator work for you. Because what is really going to happen in this first case, well, let me put what the 1. I'm going to have 1/3 times negative 3 over 8. 1 factorial is 1, so that's no problem. Now that is going to give me negative 3 over 3/8 would give you 24 over 24x. Alright, what about the second bracket here? If you want to work this out without having any problem, you can always go for your calculator, right? Let me put this over a bit more. So I have, alright, let me create that major fraction bar, and here I'm going to have my fraction. I'm going to have 1/3, so 1 over 3, open bracket, 1/3, take away 1, close bracket. Of course, I'm going to have this over 2 factorial. And I don't need to work out 2 factorial. 2 factorial is 2 times 1, so that's over 2. Now look at what I'm going to do with this part. I'm going to multiply this by negative 3 over 8x to the second power. Now, of course, x to the second power is x squared, so that's no problem. So I want to pretend as if the x is not there and put the negative 3 over 8 squared. So open bracket, negative 3 over 8, close bracket, squared. Alright, that's going to give me negative 1 over 64. So I'm going to have minus 1 over 64. I'm going to have x, this is x squared, plus, alright, let me go back to my calculator now and show you. We have actually put some things inside of the calculator already. So probably I just need to go back and adjust it. Alright, so this time it's going to be over 3 factorial. Let me come down here. 3 factorial is 3 times 2 times 1. So I can just delete this and put 6. Alright, good. Let me go back up here now. Alright, so you have 1/3, you have 1/3 minus 1. So I just need to put 1/3 minus 2. So I don't have to do this over again. Alright, so I'm going to have 1/3 here. Subtract 2. Alright, going out to this. Same concept here. It's just that instead of raising it to the second power, I'm going to raise it to the third power. So delete. Power is 3. Press equal. And that's going to give me negative 5 over 1 over 1536. Alright, so instead of having a positive here, it's actually going to be in negative. So let me delete this right here. So I'm going to have negative. I'm going to go back and look at my calculator again. That's negative 5 over 1536. Negative 5 over 1536 x cubed. Of course, I put my 3 dots because really and truly this goes on and on. And all you have to do now is multiply the expression by 2. Alright? So you have 2 here. You can multiply everything by 2. So if I multiply everything by 2, I'm going to have 2 times 1, that is 2. I'm going to have 2 times this, which is going to give me minus 3 over 12x. I'm going to have 2 times this, which is minus 1 over 32 x squared. And I'm going to have 2 times this, which is just like me dividing 2 into this, alright, 2 into 15. So I'm going to have minus 5, 2 into 15 is 7. Carry the 1, 2 into 13 is 6. Carry the 1, so 2 into 16 is 8x cubed. That's the expansion, right? Incidentally, it went down on this question, but that's my expansion there. Let's move down to the follow-up question. It says, use your answer with a suitable value of x to obtain an approximation to the cube root of 7.7. Give your answer to 7 decimal places. Alright, it's a whole lot of decimal places. So let me see what I'm going to do here. In this case, this is what I'm going to do. I'm going to go back for my expression up here, which was the cube root of 8 minus 3x. Right, so it's cube root here. Alright, I'm not even use a cube root. Let me use it to the 1/3 power, just as how they gave me it, to the 1/3. Here we have the cube root of 7.7, which can be written as 7.7 raised to the 1/3. Now, first of all, if I'm going to compare it, I need to make the two of them look alike. So 7.7, I can write it as 8 minus 0.3. Alright, that's going to give me 7.7 to the 1/3. Now, comparing these two, of course, in the place of 3x, I need to manipulate that. So this is what I'm going to do. So this can be written as 8 minus, of course, 0.3. That's easy to write because that's going to be 3 times 0.1. Of course, raised to the 1/3. Good. Now we already have the expansion, which is this. We have the expansion already for it. Alright, and we know that x is now 0.1. So what it means is that the cube root of 7.7 is simply going to be equal to when I substitute the value of x for 0.1 here, because these two expressions now look the same. So I'm going to have 2 minus 3 over 12 times 0.1 minus 1 over 32, 0.1 squared, minus 5 over 768, 0.1 cubed. All we have to do now is bring up our calculator, put all this in there. So let me just go down a bit here. So I'm going to plug all this inside of my calculator, and whatever I get is my answer. So on. So we have 2 minus 3 over 12. Alright, the 3 over 12 couldn't be broken down some more, right? That's a quarter. So 3 over 12 times 0.1 minus 1 over 32 times 0.1 close bracket squared minus 5 over 768 and open bracket 0.1 cubed. That's 1.97. Alright, so it's 1.97 1.9, alright, so I'm right, it's 1.97468. So 1.97468, and then we have 0.990, 1, 2, 3, 4, 5, 6. Well, it will be 0.99. So if I'm going to 7, 1, 2, 3, 4, 5, 6. The 9 is going to be rounded up one place, so this is going to become 1. So I'm going to have 1, 0. Alright, and this is the 7 dp. Now we can see if this actually makes sense. I'm going to go to my calculator now, and I'm going to put in the cube root of this number. So shift cube root of 7.7. Alright, so it does make sense to 7 decimal places, right? So we know we're on the right track. That's how you're going to test your answer when you're doing a binomial expansion to see if it makes sense. Alright, let's take this down some more. Okay. The next question says, given that f of x is equal to e to the 2x, obtain a Maclaurin expansion for f of x up to and including x cubed. Now for the Maclaurin expansion, let me just put it there for you. It says f of x equal to f of 0 plus f prime of 0 over 1 factorial times x plus f double prime 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed. This goes on and on and on. Now for e to the x, let me start with f of x equal e to the 2x. Now f of 0 simply means that you put 0 in the place of x. So it will be e to the 2 times 0. Anything to the 0 is 1 apart from 0. So that's taken care of. Let me go f prime of x, which means I'm going to differentiate this, right? So you know we differentiate the power. We differentiate the 2x, which is 2, which we bring to the front, and we have e to the 2x. Now f prime of 0, put in 0 up there, is going to be 2 times e to the 0, which is 1. So it's just going to be 2. Alright, f double prime of x. So you're going to differentiate 2e to the 2x. The 2 comes to the front, so you have 4e to the 2x. So you should see the pattern by now. F double prime of 0 is equal to 4. And then you're going to have f triple prime of x. So it's going to give me 8e to the 2x. F triple prime of 0 would just be 8. Alright, so you see what's happening. So e to the 2x simply going to be equal to, I have f of 0, which is 1, so I'm going to have 1 plus f prime of 0, that's 2. So 2x plus f double prime of 0 is 4. So I'm going to have 4, 2 factorial again is 2, x squared. And then f triple prime of 0 is going to give me 8 over 3 factorial, and 3 factorial is 6 times x squared. So it's almost basically like the previous one. Now, one of the things I would always like to do is to break it down to the simplest form. So you can have 1 plus 2x plus 2x squared plus 8 over 6 can become 4 over 3. I keep on writing x squared, it should be x cubed, x cubed. My 3 dots indicate that goes on and on and on and on and on. Alright, this one says show that the third derivative of g of x is given by this. Alright, so g of x is tan x. So let me start with that. G of x is equal to tan x. When I go g prime of x, I'm going to get sec squared x. Alright, we go there. Then I can go g double prime of x. So I'm applying the chain rule here, which means I bring the power to the front. Power is 2. I subtract 1 from the power, so I'm going to have sec x, and I multiply by the differential of sec x, which is going to be sec x tan x. Alright, this is really what? 2 sec squared x tan x. Alright, let's take this down some more, because I'm going to have to differentiate this already again. Alright, so what do? I'm going to have to use a product rule. So this could be my u, this is my v. Now note, I didn't have to use this as u. I could use sec squared x as u, and of course put the 2 in front of everything and just differentiate it. Alright, so this is what it's going to have. This is going to give me, I'm just doing this again so you can understand it, differential of 2 sec x. The rule says for the product rule, so let me go g double prime, triple prime of x. I'm going to have to bring the power to the front, which makes it 4 sec x. Alright, I bring it back, I subtract 1 from the power, and then I'm going to multiply by the differential of sec x, which is sec x tan x. I didn't have to do it because I did that already. Alright, and of course, you know, you multiply now by v, which is tan x, plus you differentiate tan x, which is going to give you sec squared x, and you multiply by the first function, which is 2 sec squared x. So times 2 sec squared x. Now it's time to break this down. So you have 4 sec x times sec x. That's 4 sec squared x. Tan x times tan x is tan squared x. Plus sec squared x times sec squared x is going to give me, well, times 2 is going to give me 2 sec squared, well, 2 sec to the 4. By laws of indices, you add up 2 powers, you get a power of 4. Now, is that what I wanted? Yes, all we have to do is turn this around to say 2 sec to the 4 x plus 4 sec squared x tan squared x. Exactly what we wanted, so we say QED. Alright, let's take this down some more. It says, obtain a Maclaurin expansion for g of x up to and including the term in x cubed. Alright, no problem. Let us start with g of 0, because we have written out the Maclaurin expansion already, so you know what it is. G of 0 would be tan 0, which of course when you're tan 0, you're going to get 0, so that's taken care of. G prime of 0 is going to be sec squared 0. Now sec is 1 over cos. Cos of 0 is 1. So even if you square cos 0, you're still going to get 1. Alright, so all this is just going to give me 1. Alright, what about g double prime of 0? Alright, g double prime is this. So you have 2 sec squared. Bear in mind that sec of 0 is 1 and tan of 0 is 0. So it means that 0 times anything is 0. So that's going to be 0. So that's out completely. Alright, moving to the next function. Because tan is here, automatically this part is 0. Right? The sec squared part, it doesn't matter because sec is 1 over cos, and cos of 0 is 1. So it doesn't matter what you raise 1 to, it's still going to be 1. Then you multiply it by 2. So we can actually say g triple prime of 0 is equal to 2. Now for the Maclaurin expansion, as we have written the form at the top already, it says that, I'm going to just remind you, because you need to know this, g of x was going to be equal to g of 0 plus g prime of 0 over 1 factorial. I can put this over 0 factorial plus g double prime of 0 over 2 factorial. Alright, I'm leaving out x there, x squared here, plus g triple prime of 0 over 3 factorial x cubed. In this case, this is 0, 0, plus this is just going to be x, plus this is 0, plus g triple prime, that's 2, so it's 2 over 3 factorial x cubed. So this simply boils down to x plus, alright, now this will be 3 factorial is 6, so 2 over 6 is 1/3, so 1/3 x cubed. Alright, so we have that mapped out there. Alright, let's take it down. Hence obtain the Maclaurin expansion for e to the x. So I'm going for the Maclaurin expansion for e to the 2x times tan x. What do? I have the expansion for e to the x already, and I have the expansion for tan x, and this is a product. So all I need to do is multiply them up to and including x cubed. So all we need to do is go back up, look for the Maclaurin expansion for e to the x, and the Maclaurin expansion for that was 1 plus 2x plus 2x squared plus 4 over 3 x cubed. So this would be 1 plus 2x plus 2x squared plus 4 over 3 x cubed. That's taken care of. And the Maclaurin expansion for tan x. Alright, let's go back up for that as well. The Maclaurin expansion for tan x is x plus 1/3 x cubed. So I'm going to have x plus 1/3 x cubed. Now it's imperative that we understand that we shouldn't pass x cubed. So anything that passes x cubed is out. Now everything in bracket 1 would multiply everything in bracket 2. So start with 1. 1 multiplies x, you get x. 1 multiplies 1/3 x cubed. You're going to end up with 1/3 x cubed. Move on to 2x. 2x times x is going to give me 2x squared. But 2x times 1/3 x would give me 2/3 x to the 4. That's out because we're supposed to stop at x cubed. Move to the next term, 2x squared times x. That's going to give me 2x cubed. 2x squared times x to the third power, 1/3 x, that's x to the 5. That's over it. If you move on to 4 over 3x cubed, you see that don't work because x cubed times x is x to the 4. So this plus on and on and on. Now all I need to do is look for the like terms here. Alright, so I'm going to have x in ascending order plus 2x squared. Now I'm going to have 1/3 x cubed plus 2x cubed. Alright, that's 2 and 1/3, which I can write as 326 plus 1, 7. 7 over 3 x cubed. This goes on. Now you can write a final statement that says probably therefore e to the 2x tan x equal to